So, if you see, I think I took couple of hours to explain to you the general theory of shells. First we did coordinate surfaces, I mean what you call differential geometry and how to define a surface, and then in terms of Lamé parameter, everything so far is general. I have not yet come to particular, but very soon now I will come to particular shell forms. And we have derived the general shell equations, and we have found that the general shell equations you have how many equilibrium equations? You have 5 equilibrium equations, and you have how many unknowns? How many unknowns? 6 plus 2, 8, 8 unknowns. So, obviously, the problem is indeterminate, and you will have to necessarily consider for bending analysis of shell, for bending and membrane analysis of shells, kinematics also. Kinematics means deformation of the shell also. Without that, you cannot solve the problem. So, we went on and discussed strain displacement relation, then force strain relations, and the basic equations of shells consist of, one is equilibrium equations in terms of what? Stress resultants. Basic quantity in shell theory or a plate theory is stress resultant, not stresses. Okay. Because you have transformed the 3D problem to 2D. So, only stress resultants are acting on a mid surface, okay, stress resultants, and then the constitutive relation of shells become, what is the constitutive relation of shell? See, it is not stress strain, but stress strain is transformed into stress resultant strain relations, and then the general strain relations are transformed into mid surface strains, and mid surface strains are related to displacement of the mid surface. So, it is this chain that one has to follow. So, chain is important, that you have to have stress resultants, then from stress resultants have to be related to material properties. So, obviously, you integrate the stress resultants through the thickness, and you will get your, but that will be in terms of, because stress will be related to strain at any point at point P. So, it will be related to stress resultant strain relations. Now, these strain relations can also be related to mid surface strains, and mid surface strains are related to displacement of the mid surface. So, this chain you must, or directly you say that the constitutive relation of shell is force mid surface displacement relation. If you can substitute, so it will be stress resultant is nothing but forces, direct forces and moments and shears. Of course, shears we do not define in Love shell theory, but in general it is shears. Load is shared by, load is resisted by membrane forces, bending forces and shear forces. There are 3 kinds of forces which are resisting the external load in the body of the shell. And then in the process I showed you last time that we got an 8th order partial differential equation, and you have to satisfy how many boundary conditions? 4 boundary conditions on each edge. Then again, just like plates, you had 5 quantities, 5 forces at any edge. You have N1, let us say it is alpha equal to alpha 1. So, you have N1, you have N12, you have M1 and you have M12 plus Q1 plus Q1. So, 5 quantities are there, while supposing you have to specify free boundary condition, that means all the 5 quantities must be 0. But then as per the theory of differential equations, you can prescribe only 4 boundary conditions. So, again you have the job of combining something in order to have only 4 boundary conditions on a free edge. And here we saw that it is not only shear force shear force and twisting moment which are combined, but it is also N12. N12 is what? In plane shear and twisting moment, that also is combined to form a effective in plane force and effective transverse shear force. So, we call it effective. The idea was anyway given by Kirchhoff for plates, the same thing was done by Love for resolving that issue. So, it was not a big issue. When shell theory was derived, the problem was already known. It was not a mathematical any issue there. So, it was already known. So, just it was derived that from 5 quantities we can. So, this I showed you last time. So, that is the general theory of shells. Now, the basic idea of shell is, why do you want to have a shell? Shell, the moment you give curvature, you introduce within the shell surface, within the shell element, membrane forces. If you can have a situation when membrane forces become predominantly present in the shell form, bending is very minimum. Bending, that means shear force and all these 3 M1, M1, M2, M12, they are very negligible. Anyway, shell is thin, and if you can somehow, so it is possible. It is possible that the entire external load can be only resisted by only membrane forces, provided you choose a particular form of shell and also the boundary condition. Boundary condition is very important. It cannot be done for any boundary condition. Then you will find that entire external load will be resisted by only membrane forces. And what are the membrane? Only 3 quantities, N1, N2, N12. N12 is equal to N21 in the thin shell assumptions. So, that I have already given all those things. So, this is, so let us study, because membrane shells become simpler. So, lot of people, when shell theory was difficult to solve, so they concentrated mostly on, in the beginning of the last century, was on membrane only. Analysis was membrane, because it was easier. So, such shell forms are called membrane shells, where the moment and moments will become 0. Now, moments will become 0 means what? You have your general equations of equilibrium, 5 equations I have just again stated, 5 plus 6 one also I have given, in case you, yes, about n, moment about n is this comes, but this is identically 0 provided you define this correctly. If you define this with by taking R1 and R2, then this will be identically 0. It will not be identically 0 if you make R1 one is different is okay. I mean, if you take Z by R less than unity and you neglect, you make 1 plus Z by R is equivalent to, or is approximately equal to 1. If you take that, then this is what you will get, and this is not the correct, that there is some error. This we have shown na, this will be 0 if we define these correctly with 1 by R, Z by R term. All the stress resultants having Z by R term, then this will be identically 0. If you, the moment you drop and Z by R, 1 plus Z by R is equal to 1, it will not be satisfied, left hand side will not be equal to 0. So, anyway, so that error we will, so these are your moment. So, these are the general equations, and if you want membrane, this I had already derived based upon. So, then this one, so what will happen, how to get membrane, how to get from these the equations which describe the membrane state of stress. We can just set this M12 M21 equal to 0. Obviously, the moment you put this from fourth and fifth equation, fourth and fifth means this and this. Q1 and Q2 can be expressed in terms of M1, M2, M21. So, that means these also shears also become 0. Okay. So, this one, that is what, and then you are left with these 3 equations of equilibrium. Yes, 3 equations of equilibrium. Something is, have I made a mistake? No, this Q I have separated. So, Q will become 0, first 2, third one becomes this, this is okay, because this 0, this is A1, A2 is common. So, that is okay, and this equation identically satisfied. So, you are left with these 3 equations of equilibrium. The beauty of these 3 equations is, because see, people fear differential equations, algebraic equations people can deal with, but differential equation, and that too in 2 dimension. So, this is a 2 dimensional differential equation in alpha 1 and alpha 2, and there are how many unknowns in this? How many? 3. Only 3 unknowns are there. So, one realization suddenly came to people that if you do like this, so you get a system of differential equation of equilibrium which contains only 3 unknown. So, what is the kind of problem? Such problems are called statically determinate. 3 equations means theoretically you can solve the 3 unknowns. You do not have to go to deformation, you do not have to go to kinematics in order to solve the stress resultants. These are enough to solve. So, this is one realization. So, this is one is problem becomes statically determinate, and this can be tackled directly for different forms. That I am taking now, because once you are taking a thin love, because now specifically I said let us discuss love theory. Love theory has I have kept it, they are equal. I have kept it, but then they are all M12 equal to M21. Okay, because love theory H by R is neglected compared to 1. Okay, so this one is there, and then of course, problem does not get solved, you will get the forces all right, stress resultant. So, you know the, but if you want to know the strains inside the body of the shell, then you will have to use strain displacement, and for membrane shells these are the only 3. These are the only 3 force strain relations. Force mid surface strain, they are all, see, force also is mid surface and strains also are mid surface. All these are mid surface quantities, not at any point P, it is point P naught lying on mid surface. What is K called? K is called what? K E h by 1 minus nu square. It is, where is D? Why are you confusing? But where is EHQ, my dear friend? Are we defining moment here? So, then why are you bringing unnecessary things? Axial, extensional rigidity. Axial nahi. Axial can be done only in 1 dimension. If you are talking of 1 dimension problem, then use the word axial, otherwise extensional. So, dt. So, K is called extensional rigidity, and this can be derived for every kind of material. So, that is okay, but we are doing this. So, you can get this relationship, you know. What is the other relationship which is important? See, the problem is statically determinate. So, this can be done independently now. Strain, this can be derived independently, again this can be derived independently. It is not now incumbent on you to that you have to use along with equilibrium equation. No, this can be. Then the strain displacement relation, that means strains which are defined at mid surface, all these 0 quantities are mid surface, not P naught, not P. You should always distinguish between point P and P naught. P naught is any general point alpha 1, alpha 2, z. Coordinate of P is alpha 1, P is alpha 1, alpha 2 and z, while P naught 2 dimension it is only 2, alpha 2. So, everything is brought to P naught. So, this is the strain displacement relation. Of course, you can substitute this over here right hand side. So, you will get force mid surface displacement relation, and then you can substitute this into your equilibrium. So, you will get your what? 3 equations of equilibrium in terms of displacement u10, u20 and w naught, which are mid surface displacement, 2 tangential displacement and one w. Yes, membrane does not mean that w will not be there, w will be there. Transverse displacement is there, only thing the shell somehow bending moment should cease to exist. All internal forces should be only membrane. So, we will just now see. So, this which equation? This one? What? A1 and A2, no, they are not variables, they can be defined for a particular shell geometry. A1, A2 is a property of the shell geometry. So, if you take a cylinder, it can be defined, if you take a sphere, it can be defined. So, they are not the this one. Why? No, A1, A2 is a function of alpha 1, alpha 2. It is on the surface. A2 lemma parameter are all functions of variable is okay, but it is a property of the surface. Yes, we have got only 3 dependent variables. Listen my dear friend, dependent variables. Dependent means everything is a, but this one is not unknown. This one, the moment I fix my geometry, I can find out the values of this. Okay. So, only 3 dependent variables. So, okay. Then this, so these are the basic equations. For membrane, these will be equilibrium, force strain, strain displacement, and then you please substitute this into stresses over here. So, you will get your basic displacement based formulation, which is called equilibrium equation in terms of mid surface displacement. 3 equations and 3 unknowns. You can solve, theoretically you can solve. It is a 2 dimensional problem, every quantity is 2 dimensional. So, how do you solve any partial differential equation in 2D? Normally, we assume a solution which satisfies the boundary condition. That is one of the approaches, because any differential equation must satisfy, any solution must satisfy the governing equation, which is in terms of u v w and the boundary conditions. So, we normally assume a solution which satisfies either the differential equation or the boundary condition. Now, it is easier to take a solution which satisfies boundary condition. Then we substitute that here and then we get some conditions. So, that is our standard way of solving, same approach displacement base. Okay. So, then this is okay. Yes, I have, for the sake of, although the problem is determinate, statically determinate, but still I have, for the sake of completeness, I have written. I always like you to remember that in different, how many equations are there, how many unknowns are there. how many equilibrium equations? 3. Involving how many unknowns? 3. This one, these are the unknowns. How many force strain relations? Force strain is this 3. 3. How many unknowns this involves? Because this one you have already considered in the first equilibrium. So, you cannot say that this is your unknown. So, this will be only 3, these mid surface strains. So, that is what I have written here 3, and then how many strain displacement relations? This one. Okay. So, how many? 3, and how many unknowns? You have this is already considered here. So, what is left is only u10, u20 and w0, rest all are property of the surface. So, again 3. So, you see 9 and 9 it comes. So, this you must count everywhere. If there is always if there is mismatch, that means there is some problem in your derivation of the governing equations or force strain relations, whatever it is. So, this you must check. Though the problem is statically determinate, still we have just said that yes, it can be. Now, you have to solve this governing equations in terms of displacement subject to boundary conditions, that will complete the definition of the problem. So, let us say at any edge whose outward normal is, now n is n dash, let us say something, because n we are using also for normal, normal to 1 and 2, normal to the surface also we are using n. We are talking of edge, any edge. So, that n dash can be put 1 or 2, alpha equal to 1 or alpha equal to 2. So, in general we can always write that yes, these are the this can be the boundary condition, this is a possibility. On any edge you have two boundary condition, either displacement or the corresponding force, either force or the corresponding displacement. Why? See, this is a tangential displacement. So, corresponding force is tangential force, this is the normal displacement. So, what is the u1 or u2? So, what will be the order of differential equation? 4. So, you can check, if you want to check, when you derive the governing equations of equilibrium in terms of displacement, you please check, again reduce that to single equation in single unknown. Here this will be 3 equations in 3 displacement. Now, eliminate 2, express everything, let us say only in terms of w naught or u10, or you will find it will be derivative will be 4. 4th order governing differential equation will be there. So, that of course. So, you should always see there must be this one, you should not forget any boundary condition, any number of boundary conditions irrespective of the governing difference. No, there must be some relationship. So, if it is a 4th order, so only 2 here, boundary condition 2. Normally, it is if nth order, nth, so it is n by 2 and n by 2. It is called even order boundary value problem. We always get, we are lucky in solid mechanics, we always get even order, even, n is always even. All our problems are such that governing equation, anyways there is no boundary value problem with single OD, I mean first order ordinary differential equation. You need minimum 2 edges even in one dimension. So, 2 edges means minimum second order ordinary or partial differential equation is required, second order. Now, but then you want to satisfy boundary condition at one edge, how many? If it is second order, 1 and 1 minimum, third order. I have told you already, my dear friend, fluids, yes, you get. I am saying solid mechanics. Only in solid mechanics we get even order BBP. in solid mechanics. Is it okay? Why you get, I do not know, I do not have answer. You find the answer then. Nobody has yet come across a problem in solid mechanics where the governing equation is odd ordered. It is always even. Okay. So, that is one good thing. Now, what is normally okay? So, this I have defined now also a membrane in theory. I have not yet taken any problem, because first I wanted to complete the general theory of bending as well as membrane. Now, what should be membrane is simpler to solve. So, I think we will do something, and what is normally the solution strategy, because you are interested in solution, not so much of equations, how to solve. So, if it is membrane, first I think you can deal with our equilibrium equations, which are in terms of stress resultants N 1, N 2, N 1 2. Please solve it and get N 1, N 2, N 1 2 as a determinate problem. We can have some approaches to find out N 1, N 2, N 1 2. Once you have found out the stress resultants from first, it is not possible in a general shell, it is possible only in membrane shell. General shell you will have to, yes, there you have to, of course. So, then once the stress resultants are known, the strains can be obtained by inverting the force strain relation. See, we had one this relation, this one, k to why the kh I have, so EH I have written. So, this is okay. I think new goes must be going something. Is it okay? Just see N 1 by so this 1 minus nu square will not come, no, it has gone only. So, if you want to express in terms of k, then something will come, otherwise if you want to put it in terms of EH, so it will come like this. Is it okay? It is okay? Okay. So, this is you get this, because these ones are already known. So, please find out this. So, this will be number 2 step. By the way, strains are displacements are continuous in shell unless there are some defects or cracks, and so strains also will be continuous and single valued. So, then 3 go back to your this relation, this one. Now, left hand side is known, now right hand side is not known. So, this will go on the other side known. So, all these quantities are known. So, that is what I have written, this in general right hand side, all these are known, these quantities are known, this is known, and you have got 3 equations in 3 unknowns only, u10, u20, w0. So, we can get the displacements. Of course, this will involve also integration, this is important, some, because this is derivative of displacement is there here. So, you will have to integrate, some integration is required in order to get displacements. So, this is the normal solution strategy, and what happens I have one slide. What is your interpretation of membrane? Normally you will say this, na. One supposing you go from the bending side. So, you will say that bending rigidity of membrane shell should be very small, negligibly small compared to extensional. It should be very stiff in extension or compression, but bending, so real membrane very thin, thin, just like membrane, a cloth or whatever you have seen membrane, a rubber, your balloon is a membrane. Okay. So, this is, and it also gives you, because if H is thin, this is to the power cube, E H cube by 12 1 minus nu square. So, if this is thin means mathematically we always take less than unity. Yes. So, cube means it will be very small quantity. So, this d becomes very small, while this one is only a order of h. So, this will be bigger, this will be bigger. So, this will be very small, this will be bigger. So, it is okay. So, when the shell is thin, that can behave. We can also say there is another way of interpretation. How do you define a membrane? Which we may argue that a membrane shell is one in which changes in curvature or twist. See, if you load it, let us say there is a shell and you load it, it becomes like this. That means, the radius of curvature at points have changed. The moment radius of curvature will change, bending will come in the picture. So, you have a form and some boundary condition in such a way that when you load it, it retains its shape, no changes in curvature, because curvature is given by this. These are the three terms which says changes in, I think I have explained, these represent changes in curvature from the original to final. So, this one, so changes in curvature, so this must be very small. So, you can also, when you go see a shell form, and you can see, yes, no, this is more or less behaving as a membrane, because when the load is there, I have put my boundary condition in such a way that it is, there is no change in curvature. So, this is the gist of membrane behavior.